Welcome everyone. In this video lecture, we will think about the kinetics of oxidation, which is basically called the deal and group model. Okay, so in this deal and group model, we have to find the kinetics of the oxidation. Okay, so we will discuss it in detail. So the very first thing that we have to think about here, we are saying there is a silicon substrate. So I am just saying, say this one, this side is our silicon substrate. Okay, this side is basically our silicon substrate. Okay, and after that there is a oxide formation. Silicon dioxide, SiO2, is formed when it is put in the oxygen ambient. So this side is our silicon oxide layer. Okay, we will discuss what is F2, F1, everything. So this one is our silicon oxide, and this side is our gas. Okay, this side is our bulk. Sometimes we call it bulk. Okay, gas or gas, even we can say this is our gas. Okay, this side is our gas. Okay, so SiO2 formation, then it is the surrounding. Okay, which is the basically the gas. So here we have written so many things like Cg, Cs, C naught, Ci, C star, F1, F2, F3. So what are these terms that we will discuss first? So the very first thing, that is our Cg. So Cg is basically the concentration of oxygen, the oxidizing species in gas. So this one is nothing but simply the concentration of oxygen. Okay, concentration of the oxygen, or we can say the oxidizing species in gas. And then after this Cs, the Cs is nothing but simply concentration of oxygen, that is our oxidizing species, near to the gas and oxide interface. Is it okay? Concentration of the oxygen or oxidizing species near to the surface of gas and silicon dioxide interface. Okay, the third one the third one is our C note. So C note is basically the concentration of, again, oxygen, oxidizing species at the outer surface of the oxide layer. Okay, at the outer surface of the oxide oxide surface. Okay, and the final one more thing, Ci. This Ci denotes the concentration of the oxidizing species at the inner oxide surface. At the inner oxide surface. So this one is the concentration of the oxygen, oxide or oxidizing species at the inner oxide surface, and C star is the, we can say, the equilibrium concentration of the oxide. Okay, so these are the five things: Cg, Cs, C star, C naught, and Ci. So concentration of the oxidizing species. Okay, this one, concentration of the oxidizing species in gas, concentration of the oxidizing species, which is oxygen, at the gas and silicon oxide interface. Okay, and C naught is the concentration of oxidizing species near, at the outer of the oxide surface, and Ci is the concentration of oxidizing species at the inner oxide surface, and C star is the equilibrium concentration in oxide. Okay, so this one is the rough idea about all these things. Now the other thing, that is our F1, F2, F3 are the three fluxes. Okay, F1, F2, F3 are the three fluxes. Okay, F1, F2, F3 represent the three sequential steady state fluxes at the oxidizing species. Okay, so from that one, F1, we will start what is F1, F2, F3 in detail, and at the steady state, F1, F2, F3 will be same. Okay, at the steady state, this F1, I am writing here, At the steady state, this F1 equals to F2 equals to F3. Okay, now we have to start with the F1. What denotes F1? So F1 is basically the flux from gas to oxide. So here I am writing F1. So F1 is nothing but simply flux from gas to oxide. Okay. So this one, the flux from gas to oxide is nothing but simply transport of the oxidizing species. We can write it. I am writing here. Then we will discuss in more detail. Transport of the oxidizing species species from the gas to the surface surface of oxide. That is our SiO2. Okay, F1 flux is nothing but simply transport of the oxidizing species from the gas to the surface of the oxide. Okay, so flux F1, this flux F1 can be written as H, okay, G. Then after we can write it Cg minus Cs, where Hg, where this Hg is nothing but simply the, what we can say, the Hg is the transport, sorry, Hg, what we can say, Hg is the proportional constant, or we can say the gas phase mass transfer coefficient. Gas phase mass transfer coefficient. Some coefficient. Coefficient. Okay, Hg is nothing but simply gas phase mass transfer coefficient. Is it okay? Hg. Clear? So the first formula that we have observed, that this one is our, the flux F1 is nothing but simply Hg into Cg minus Cs. Cg is the concentration of the oxidizing species in the gas minus concentration of the oxidizing species at the at the surface of the oxide interface, gas and surface of the oxide interface, and Hg is the sub constant, proportionality constant, that is our gas phase mass transfer coefficient. Okay, so this one is the F1 flux. Okay, now what we can write, this Cg, I am writing here, this Cg can be written as Pg upon Kt, and this Cs can be written upon Ps by Kt, where this Cg, concentration of the oxidizing species in the gas, is partial pressure of the gas by Boltzmann constant into temperature, Cs Ps by Kt. Okay, so basically this formula, if someone will ask how this formula is coming, so I have already made a separate video on this one for the concentration as a function of pressure, Boltzmann constant, and temperature. Or this can be also easily observed by the ideal gas equation, that is our, if we know Pv equals to nRT, the ideal gas equation. Okay, I am writing here ideal gas equation. From this ideal gas equation, what we can write, this pressure, the P represent the pressure. Okay, I'm writing here. P is the pressure, V the volume. Okay, I will go. N is the amount. Amount is basically in mole. Okay, volume in meter cube. Pascal, we can write it Pascal. Okay, R is the gas constant. Gas constant, and this value is 8.31 joule per Kelvin per mole, and T is the temperature. Okay, okay. So now this one is the ideal gas equation. So PV equals to nRT. I am just going to solve this one. Cg equals to Y, Cg equals to Pg by kT. So one can simply write this P equals to nRT by V. Okay, now once again, this n, this small n can be written as n by Na. We can write like R by V into T. What I am writing, one more formula that we are going to write, this n equals to capital N by Na, where n is the number of gas molecule, number of gas molecules upon Avogadro number. Okay, we are going to prove this one. Okay, how I am writing this. Okay, for this purpose we have started from the ideal gas equation. Okay, so P equals to this we can write, then P equals to this we have written, because N can be written as Na by A. Okay, so then after this N by V is nothing but simply, then P can be written as N by V R by Na into T. So it should be N by V is the concentration, R by Na is our Boltzmann constant, T. So this P is CKT. Okay, where C is the concentration, K is the Boltzmann's constant, and this Boltzmann constant K value is nothing but simply R by Na. If we solve this R by Na, 8.31 joule per Kelvin per mole upon Na. Na is what? Avogadro number. So we have to know the value, 6.10 to the power 23 mole inverse. Okay. So if we solve this one, we will definitely get 1.38 into 10 to the power minus 23 joule per Kelvin. Okay, this mole and mole will be cancelled. K value is simply our 1.38. Okay, so this one is our P equals to CKT. So simply we can write this C, okay, this C equals to P by KT, that we have already derived. Okay, so this one is the proof of this one. Okay, so why we are doing all this thing, it will be clear very soon now. So F1 equals to HgCg by Cg minus Cs. I am saying this one is our equation number 1. Okay, equation number 1. So now this F1, that is, I am writing here HgCg minus Cs. Now this Hg, make it Hg. Okay. Now Cg can be written as Pg by Kt minus Ps by Kt, and this can be written as Hg by Kt Pg minus Ps. Is it okay or not? Now we have written the concentration in terms of partial pressure Pg minus Ps. Okay. Now again there is a very important theory, that is our Henry law. Okay. So I am writing here. Say this equation is our two. Equation number two. Okay. This one was the our equation one. We have write it like two Henry equation. Okay. So now from Henry law, what is Henry law? We have to know the concentration of a species, okay, within a solid is proportional to the partial pressure. I am writing the concentration of a species within a solid is proportional to the partial pressure. Okay, partial pressure. Okay, so partial pressure of surrounding gas, of surrounding gas. Actually, we are going to simplify this equation in terms of concentration. Okay, C star, C naught, Ci only. Okay, so this can be written as the equilibrium concentration. The value, that is our C star, is some constant, proportionality constant, into Pg, and the another one, C naught, can be written as H upon Ps, partial pressure at the surface. So now we have to put the value of Pg as C star by H, and from here the value of Ps can be written as C naught upon H. Okay, now we have to put in equation F1. Okay, so finally the F1 can be written as Hg by Kt C star by H minus C naught upon H, or we can write it Hg Kt H C star minus C naught. Okay, and this whole term is somehow a constant, so I am writing the proportional constant H C star minus C naught. Okay, so generalized function for, we can say, the F1 value is nothing but simply H, equilibrium concentration of the oxide, minus oxide's surface. Oxidizing means concentration of the oxidizing species at the oxide outer surface. Okay, so the F1 flux can be written as, the F1 flux can be written as like this. So somehow in many book, it is directly they are writing like this: F1 value, the F1 value will be simply our, okay, simply H C star minus C naught. Okay, so this is all about the F1. We have focused only on the F1. Okay, so the F1 value will be H C star minus C naught. Now we have to think about the F2, that is our flux through the oxide. F1, the flux from gas to the surface of the oxide. Now F2, the flux through oxide. Okay, so we have to write F2. I'm writing here F2 flux through oxide. Okay, I am highlighting this one. I will go with full details and I will try to solve each and every line with full justification and full mathematics. All okay. So F2 is nothing but simply flux through oxide, and in this case there is a diffusion. So we can write it. This flux is associated with the diffusion of that is which is basically the governed by the Fick's law. So diffusion of the oxidizing species, a species from the gas to the surface of the oxide, surface of the oxide. Okay, and we can say this is say equation number A. I am writing like A. This is the main equation. We can say F1 is a H some constant, then C star minus C naught. Okay, initially we have started with the what, Cg minus Cs. Now instead of, because so many variables are there, so we have to focus only with three variables: C star, the equilibrium concentration, Ci, C naught. So that's why we have eliminated the uh, Cg and Cs. Okay, we have to eliminate this one. Okay, we have to eliminate this one. Clear? So only we have to focus only on these three. Okay, so F1 we have written as terms of H C star minus C naught. So how it is coming? We have solved, okay, by using the ideal gas equation, then the Henry law, then it should be H C star minus C naught. Okay. Now the diffusion occurs at the oxidizing species from the gas to the surface of the oxide. Okay, so here the diffusion occurs. Okay, so if this one is a diffusion case, so in diffusion F2 can be simply write as, okay, blue color I am taking, d some F2 dc by dx. Okay, d gx by this, yes or no, d diffusion constant dc by dx. Okay, and this value will be simply, or one can also write d c naught minus what, oxide surface, this one c naught to ci, so c naught minus ci by x, some with I am saying x, so you can write as this. Okay, d f2 equals to d dc by dx. Okay, so this we can write like this. Clear? So now we will go for the detail. So basically it follows the Fick's law. Okay, it follows the concept of Fick's law. Okay, Fick's law. So what we can write directly, we have already written. So F2 can be written as some diffusion constant dc by dx. Okay, so d will be same, concentration change, so c naught to ci upon the width. Okay, the change in the width is x. Okay, d c naught minus ci by x. Okay, where this f2 is nothing but simply the movement of oxidant through existing oxide layer. Okay, here also I am writing one more line. F2, this F2 is related to the movement of oxidant movement of the oxidant through existing oxide layer oxide layer. Okay, so basically it diffusion occurs to the oxide layer, and diffusion is proportional to the concentration gradient. Diffusion is proportional to the concentration gradient. So this one is the equation number, we can say this one is say equation number B. Okay, so this equation is also important. So F2 is this. Okay, now last one is our flux F3. Okay, F3 is this F3. So this F3, okay, this F3 is nothing but simply Ks Ks into Ci, rate constant into Ci in this solid, what, in solid surface of the silicon. So F3 we have to write. Here I am writing F3. So F3 is the flux of reaction. Flux of reaction, we can say. Flux of reaction. So in this case, the chemical reaction happens. Okay, so I'm writing the chemical reaction of the oxidant with silicon silicon, simply we can write silicon at the SiO2 interface interface, and it is proportional to F3 is equals to simply KSCI. Okay, this one is the Fs equals to KS. Okay, this I am saying equation number C. Equation number C. So now at steady state, under steady state condition, all three equation A, B, C will be same. Okay, so I am writing here under steady state condition. Okay, these fluxes are equal. F1 equals to F2 equals to F3. Okay, so now we have to think and we have to solve this F1 equals to F2 equals to F3. Okay, so the first thing now we have considered F1 equals to F3. Okay, so now I am considering first one F1 equals to F3. Okay, so what we can write, F1 is H C star minus C naught, and F3 is KSCI. Okay, now from this equation can we find the value of C naught? Okay, so for this one what we can write, one more line, HC star minus HC naught equals to KSCI. Okay, and once again we can write HC star minus KSCI equals to HC naught. Okay, so C naught value can be written as HC star minus KSCI by H. Is it okay or no? From here we have find the value of C naught as a function of C star. Okay, and here we are considering F1 equals to F3. Okay, so A and B, we are taking A equals to B. We are taking equation A equals to equation B. Okay, and then we have find this. Now what we will do? We will take F2 equals to F3. So now from F2 equals to F3, C naught is known to us as a function of Ci, and equilibrium concentration is there, C star. So we can find the value of Ci or C naught. Okay, directly. So we will go for the next page. Okay. Okay. So once again I am writing that what we have observed first F1. The value of F1 H H C star minus C naught. Okay, that we have observed. F2 is nothing but simply D times of what? C naught minus Ci by X, the width of the oxide layer. That is our equation number B. And F3 equals to Kh times of Ci, equation number 3. This one is the main equation that we have find. Okay, these three equation A, B, C. Okay, now what in the earlier page what we did, see, F1 equals to F2 first. Okay, okay. So in the first thing, once again I am writing F1 equals to F3. Okay, from F1 equals to F3, after solving F1 equals to F3, we have calculated C naught as a function of H C star minus KSCI upon H. Okay, clear? This one is also we have find. Okay, now what we have to do? We have to go for the F1, sorry, F2 equals to F3. F2 equals to F3. So from this one, what we can write? D C naught minus Ci upon X equals to KSCI. Okay. Now C naught is known to us. Okay. So can we find Ci? We can easily find Ci also. So for this purpose, we will go for the step by step. D, what we can write? C naught minus DCI. Okay, we will go each and every step. KSCI X. Okay. Then after we can write D. Okay. If we take D here and write C naught. Okay. D common, and instead of C naught, what we can write? H C star minus KS CI upon H minus CI. Okay, can we write? Okay, minus CI. Okay, or we can also do one thing, instead of this and CI, take common here KSX plus D. Okay, we have to put we have to take this one in the right hand side. So D C naught. C naught is nothing but simply this. See, this C naught is nothing but simply this from equation, say, uh, equation D. I am saying equation number D. Okay, this we can write. Now D H C star by this. Then again we have to do some solution. So d c star minus ks ci by h ci ksx plus d. Okay, one more line we will write. Now dc star. Okay, and this term we will put in the left hand side. So ksx plus d plus ksci d upon h. Okay, ksx plus d plus kxci d. Okay, just solution d c star at the left hand side and d ksci h in the right hand side. So the value of ci, okay, directly we can write the value of ci is nothing but simply d c star upon ksx plus d plus ksci d by h. Okay, and if we cancel the d, okay, one more line I will write. If we take d common, 1 plus ksci by h plus ksx by d. So this d and d will be cancelled out. So ci value will be here as a function of equilibrium concentration of the oxide, 1 plus ksci by h plus ksx by d. Okay, so this one is the ci value. Okay, now ci is known to us, so we can directly write the c naught value also, because ci is not now known to us. So okay, so this one I am saying this one is equation number e. Okay, so now from here I am just using this formula here. If we put the value of sorry, right first, c naught equals to, this one is c naught h c star minus ksci upon h. Okay, so c naught can be find by putting the value of ci. So ci we have already find this one, this value we have to put here. Okay, so and this one from equation number d. So now ksc star upon 1 plus ksci by h plus ksx by t. There is some simple solution we have to do it. Okay, then c naught equals to n whole divided by, okay, wait, this we have to put it and this h instead of ci, this h. Okay, so c naught will be hc star 1 plus ksci. Simple solution is there, ksx upon d minus ksc star upon h upon 1 plus ksci by h plus ksx by t. Is it okay? Okay, now this c hc star. Okay, and if we multiply the whole term with hc star, so h is there. Okay, so what we can write, hc star, this hc star is there. Okay, and this one is KSCI. Okay, KSCI. So this one will be cancelled by KSH. Is it okay or no? KSH. Okay, if you multiply this one, simply I am multiplying HC star plus KSCI C star plus HC star X by D. Okay, minus KSC star. Okay, is it okay or no? HC star. Okay, 1 plus KSC. Okay, C. Oh, sorry, this CY will be not be there now. Okay, 1 plus KSH by CI. Okay, wait. KSH. Okay, okay. KSH. CI is already common. Okay, sorry. So this should not be KST. No? KST. Okay. There will be no CI. Sorry. There will be no CI. KS by H. Okay. KS by H by KS X by D. That's why it is not. I am unable to cancel. So now this one will be no CI. Okay, sorry for the mistake that I did. Okay, KSH. Okay, so HC star once again KS 1 plus KS. Okay, CI will be not be there. So HHKS into C star, KS into C star. Okay, so it should be KS into C star. This okay, I just eliminate. Okay, there is a mistake. This should be K C D C star and CI we are taking common. So KS X plus D plus KSD by H. Okay. See KS once again. Okay. Nothing will be there. Okay. So CI is nothing but simply C star upon 1 plus KSH upon KSX by D. Okay. C star upon 1 plus. So the C naught value will be after putting this H C star 1 plus Ks by H plus Ks x by D. Okay. So see H C star H. So this will be cancelled out. Now I can write H C star plus Ks C star plus H Ks x by D minus Ks C star upon H1 plus Ks by H plus Ks x by D. This one is the so this should be cancel out. mm, Ks C star. So and H is also common in everywhere. So we can write it C star. Okay, in bracket 1 plus. Okay, this one is also K S X into C star. Okay, C star then common 1 plus Ks upon D. Okay, into X. Ks X by D. H will be cancelled out. So this should be 1 plus Ks by H. We have to be very careful in all these calculation. So final expression that we already find the value of CI, the C star upon 1 plus Ks by H plus Ks x by d, and C naught equals to C star 1 plus Ks by d into x upon 1 plus Ks h plus Ks x by d. Okay, so this one is the Ci and C naught expression. Sorry, I did some mistake, that's why there is a delay. Okay, Ci and C naught is now known to us. Okay, now what we have to do, this we have already find. Okay, now what we can do, again I am just drawing to, okay, it will be fine. Now as we know, this side is our Si or 2. Okay, so now when we are saying the diffusion, mm, we can say case 1, when if the diffusion, there is no diffusion limited. Okay, diffusion is limited. So during that time, diffusion is limited, d tends to 0. So this value will be 0. So it should be infinity. Infinity, so Ci is simply our 0, and C naught will be C star. Okay, oxide concentration. Okay, D0 means it is infinity, so C star by infinity is 0, and D is again infinity infinity. So if you solve this one, it will go for C naught equals to C star. Okay, clear this thing? Clear? Now, because this D is what, 0, so infinity. Okay, so you have to take the d term common, and if you solve, it will come C naught equals to C star, which is our diffusion limited condition. And case 2, if d is tends to infinity, d tends to infinity, so x by d is very small. Okay, x by d is infinity, so x by d is very small. Okay, so then in this case, ci equals to c naught, and it is nothing but simply c star by 1 plus ks by h. Okay, so one case, that is our ci equals to c naught. Okay, and in another one, ci equals to 0, but c naught is c star, and in that case both will be, when diffusion is, d is infinity. Okay, but when d is 0, so it should be like this. Okay, so this is the all about the concentration of the oxidizing species at the inner oxide layer and the outer oxide layer as a function of equilibrium concentration of the oxide and the diffusion constant d, and x is the width of the oxide layer. Okay, and ks is the reaction rate constant. Okay, and h is the gas phase mass transfer coefficient. So this we have calculated. Is it okay or no? There is some calculation is there, but if you practice 2 or 3 times, then it will be more clear. Okay, so up to this is clear, means we have started from this. Okay, just as a summary, I want to write summary, means there are three fluxes, F1, F2 and F3. Both will be, all will be same. Now from this one we have come to the conclusion of what, Ci, first Ci and C naught. Okay, Ci we have calculated it C star upon 1 plus Ks by H plus Ks x by d, and C naught is little bit complicated, but 1 plus Ks x by d upon the 1 plus Ks H plus Ks x by d. Okay, this one is the two formula we can say. Okay. Okay, so after that, this one is the equilibrium concentration, all these things. But now we have to find the oxide growth. Okay, now we have to find out the oxide growth. Okay, to find out the oxide growth, what we have to do, that we will now discuss. So for this purpose, we have to write oxide growth rate. Okay, so here I am writing oxide, at what rate the oxide is developed. Okay, so before that we have to assume that, or we have to write, let n1, okay, is the number of oxidant molecule per unit volume of oxide. Okay, let n1 be the number of oxidant molecule at volume of the oxide. So oxide growth rate, so that can be written as n1, okay, dx by dt equals to flux 3 ksci. Okay, that is our f3. Clear? So now once again we can write n1 equals to dx by dt, and ks instead of ci, what we can write, ca star upon 1 plus ks upon h plus ks x by d. Okay, this one is the generalized form. Now we have to go for the calculation of this. So what we can write, one can write 1 plus ks h plus ks x by d. Okay, the whole denominator term into dx. Okay, and now another thing, then ks by n1, ks by n1 c star dt. Okay, all are constant. So, or we can also, if you can write like this also, dt integration, this one dx variable separable. Okay, and this. Okay, now this whole term can be, we have to integrate the 1 plus ks by h. So one can be write as 1 plus ks by h x plus ks by t x square by 2, x square by this one is d, x square by 2 equals to ks by n1 c star is the constant, so dt integration t plus some integration constant, this p is some integration constant, integration. Is it okay? Simple integration, and we have come to the conclusion, 1 plus ks by h x ks by d x square by 2 plus this in. Okay, now we have to find the value of p. To find the value of p, we have to assume that, let the oxidation started, oxidation started started, then the initial oxide thickness is xi. During that time, the oxide thickness is xi at just time t equals to 0. Okay, when the oxidation started, the initial oxide thickness is xi at t equals to 0. So from this one, we can find the value of when t is 0. Okay, so p value, the integration constant will be 1 plus ks by h into xi plus ks by d xi square by 2. Is it okay? By 2, or ks by this will be 2. 2. Okay, so now this one is the integration constant. So now we have to go for the, I think, next page. We have to go for the next page. Okay, so basically in the oxide growth rate, we have started with this n1 dx by dt equals to f3 ksci, and after solving this we will get a integration. Okay, like all this after putting the value of ci. Okay, that is our ksci c star. Okay, 1 plus ks by h plus ks x by d. Okay, clear this one. We come to this one. Okay, and then after the integration and all, what we will get, the final expression in the previous page, ks by h x plus ks x square by 2d equals to ks c star by n1 into t plus some p, some constant, integration constant. So that integration constant we have find for t equals to 0, and during that time the oxide thickness is xi. So the value of the p that we have already find, 1 plus ks by h xi plus ks by 2d xi square. So we have to write the value of p here. So one more line, because this one, in this one, very uh, complex calculation is there. So I am going to write each and every line. C star by n1. Okay, mm, t plus p we have already written here, 1 plus ks h. Now here it is xi, not x. Okay, this is some fixed value, so 2d by xi whole square. Okay, this one is the term. Okay, so here the you have to take the variable x square, xi some fixed value we have assumed that fixed value at t equals to 0, oxide thickness is say xi. So now what we can do, x square is there, so we have to focus about x square. So if we multiply the both side with 2d by ks, on on dividing both sides with 2d by ks. Okay, so what expression we will get? What expression we will get? First we will get x square plus x 1 plus ks by h. Okay, both side by 2d by ks. Okay, so it should be 2d by ks x 2d by ks multiply with 2d by ks. Okay, these two is okay now. 2d by ks, so ks will be cancel out. C star t, c star t into 2d by ks n1. Okay, c star t into 2d by ks. Okay, oh sorry, ks will be cancelled out. Here also we have to multiply with 2d ks. So ks multiply, cancel out. So c star t by 2d by n1. Okay, plus xi square, simply xi square plus 1 plus ks by h xi into 2d by ks. Is it okay? This one, this line. Okay, so now for the simplification purpose, this we can write as ax bt plus xi square 1 plus ks h 2d by ks, where a is nothing but simply 1 plus ks h into 2d by ks, and b equals to this b. Okay, bt means c star 2d by n, or 2d c star by n. Okay, so bt, this expression. Okay, now once again, is it okay? This one a, instead of this I am saying, okay, I am highlighting this one. This one I am saying a. Okay, a. See, now for b, for this b, this, okay, c star 2d by n1. Okay, n1. So better to write n1 here. Okay, x square plus ax plus this. Okay, now once again, for more simplification, one can also write x square ax plus b, in bracket we can write t plus tau. Okay, p, t plus tau we are writing, because this b t plus tau, because bt plus xi square plus this whole term. Okay, where this tau can be written as xi square plus axi by b. Okay, for simplification purpose, this term is tau. Okay, xi square plus 1 plus ks by h 2d by ks is b t plus tau. Okay, so this equation is our x square equals to ax plus b t plus tau, where tau equals to xi square plus axi by b. Okay, just for simplification we have written like this. Okay, so this is the deal and groove kinetics equation of oxidation. So this one is the deal and groove kinetics equation. Okay, kinetics equation. Okay, so now if we come to this position of x square ax plus bt plus tau, now this x is the actual oxide thickness. So this x can be written as minus a plus minus b square minus, means minus minus plus, so 4 b t plus tau by a 2a, sorry, 2. So a is 1, so 1 we can write. Okay, now we have to go for two, what we can say, two consideration, two case we can say. Oxidation for a very small time, oxidation for a very small time, or t tends to 0, for duration t tends to 0. So at that time x equals to what we can write, minus a plus minus this, if we take common a outside, t plus tau by 2. And for t tends to 0, for very small thing, what we can do, we have to just take the 1 plus x to the power 1 by 2, where x is very very less than 0, means x is nearly very small quantity tends to 0. Okay, so if we solve this one, minus a plus minus a 1 plus 4b by a square t plus tau into 2. Okay, by 2. So this a and a will be cancelled out. So what we can write, 4b t by a. So this 4b by 4b, sorry, this should be 1 plus, if we solve a plus 4b by 2. So this 2 to 2b, 2b. So it should be bt. Okay, so b by t and a t by tau. If we solve this one, okay, we will go for the full detail. Minus a plus minus a 1 plus 4b by a square into 2 t plus tau with more terms. Okay, by 2. So if we solve this one, this a and a will be cancelled. Only we have to take the plus one, because it it may not be the negative one. So minus a plus a plus this one is 2, 2b by a square into a is term is there, and t plus tau by 2 by 2. So these two cancel, these two cancel, a cancel, a cancel. Okay, b by a t plus tau. Okay, simple one, t plus tau, where x is linearly proportional to time. Okay, so here x is linearly proportional to, here x is linearly proportional to time. Okay, now the next one, case 2, when t tends to infinity and time is very high. Okay, then in that case x equals to minus a plus a in bracket 1 plus 4b by a square t plus tau, t plus tau by twice. Okay, so is much greater than 1. So after solving this one, it will come x equals to root bt. So this x equals to root bt is the parabolic rate constant. So this one is simple calculation is there, and this one is our linear rate constant. This one for time, very large time infinity, and this one for t equals to 0. So this is all about the Deleuze kinetics equation. uh, of oxidation. So in the last, you have to be some practice for this one. So but finally it will come. So for more detail, you can also go for Dylan group model. Okay. Uh, a means for the final, okay, verification of deal group kinetics, we have to be very careful, and we have to go very step by step manner for the final solution. Okay, so thank you for watching this video. Thank you.